Okay, today we are going to talk about a newer model of the atom, which is the quantum model of the atom. Now, before we move on, we kind of got to back up again because the last part that we left off on was Bohr's model. And there were a couple of questions or problems related to Bohr's model. And if you remember, Bohr's model had a nucleus in the middle, and then we call it the planetary model because it kind of had these electrons orbiting. But here were the questions. Number one, why excuse me, did electrons only exist in certain orbits? Okay, so why were there only fixed patterns? And secondly, why couldn't there be a limitless number of orbits of slightly different energies? So although we knew that these differences existed, how come we couldn't have all these other little orbits in the middle that kind of filled in the empty space? How come there were only these fixed patterns? Okay, and we will also take some time to review all of the atomic models that we've talked about in class. So we'll get there on this stuff the next time I see you. Okay, with quantum theory, remember, theory is an explanation of something. That's what how we define it in science. And quantum theory, what it attempts to explain is the wave properties of electrons. And I'll get there in just a minute as to why we can treat electrons like waves, but it uses a whole lot of math. Now, we got to ask you to make several leaps here in this section because we're not going to learn the math. We just need to kind of understand the final result. And the way that the analogy I make is that in geometry, they always have proofs that lead you to this last equation. And really what we're going to do is we're going to skip the proof. We're just going to go to the equation on this. So, okay, one of the guys to come along that was important is Louis de Broglie. And what de Broglie said is, let's treat electrons like waves. Okay, essentially what he did was, if it took Einstein to say, let's treat light like particles, he said, let's treat electrons like waves. If Einstein said, let's treat light like particles, he just flipped it around. And what de Broglie said is that we can view electrons as little waves confined to the space around the nucleus. And again, you don't necessarily have to understand why he explained it that way, just that he could. But those waves could only be certain frequencies. Okay, remember, frequency is 1 over s, or hertz, since electrons can only have certain amounts of energy. Okay, and remember our equation for energy, where we had E equals Planck's constant times the frequency. So now, if electrons behave both as waves and particles, we still had this question, where were they in the atom? Okay, now Werner Heisenberg came along in about 1927, and the dates are important. You do need to know these. It's really the order, but because I need you to know the order, yes, we need to know the dates. And he said electrons can only be detected by their interaction with photons. And that it's impossible. What he's famous for is what's called the Heisenberg uncertainty principle, which states that it's impossible to know both the position and the velocity of an electron, that's an at symbol, at the same time. Okay, and if I come back to this photon thing for a second, remember, if electrons get excited, they go up energy levels. Well, as soon as they come back down, because they don't want to be there, they give off these photons, and these photons that are given off are how electrons can be detected. So he really was just, got credit for just being able to say we can't know both the position and the velocity of an electron at the same time. And then along came Erwin Schrödinger in 1926, actually a year earlier than Heisenberg. But what he did was he came up with what's called the Schrödinger wave equation. He also had a great problem called Schrödinger's cat, which we'll talk about in class. But what he did is he stated that his equation essentially proved that electron energies are quantized. And I should use a different word besides proved. I should use supported or provided evidence for. Right, because we try not to use proved in science in case something new comes along. So anyway, his equation supported the idea that electrons are quantized. Now Bohr had assumed quantization in his model. Okay, remember quantums are just certain amounts or packets of energy. And Bohr just made pretty much a leap, and he turned out to be right. So it shouldn't be discredited. Someone came along and gave the evidence as to why that quantization could occur. And again, part of the solution was that only waves of specific energies actually worked in his equation. So we have this whole idea of specific energies and specific frequencies being the answer, so to speak. All right, now with the Schrödinger wave equation, we had a little bit of a dilemma though, is that his equation still only gave a high probability of finding an electron in a certain location. We still couldn't nail it down. And that a certain location is what we refer to as an orbital. Bohr had orbits, just like the planets, right, where things go around something. Okay, an orbital, and this is orbits are 2D. They're 2D paths. An orbital is a 3D area around a nucleus that has a high probability of containing an electron. And I like to think of them as little balloons that surround at the nuclei, and we'll see this. And they have different shapes and different sizes that we eventually will need to be responsible for. Okay, the last thing we got to talk about is kind of an abridged version of quantum numbers, which essentially provide the electron's address in an atom. And they specify the properties of atomic orbitals and of the electrons in those orbitals. There are 4 total quantum numbers. The first 3 numbers come from the Schrödinger equation and describe the main energy level, the shape of the orbital, and finally the orientation of the orbital. And that's really just where they are in space. And I like to think of this as an address where if we refer to or compare the main energy level to the town, there's lots of electrons that can live in the same town or the same main energy level. The shape is going to start to narrow it down. So you may think of that as like the electron street. Lots of electrons can be in the same shape, different shapes of orbitals, and lots of people can live on the same streets. Orientation may narrow it down a little bit more, for example, on an address as to which house. And then we are also going to have a 4th quantum number that's going to describe the spin state of an electron. And this might be the room of which house. So once you get through with these 4 quantum numbers, you have a specific spot of where an electron may be in that atom. Just like with an address, you know, the town, the street, the house, and ultimately the room in that house is going to define where a person lives. So okay, the first quantum number that we're going to talk about is going to be the principal quantum number n, and it is going to describe or define the main energy level of an electron. The values are all going to be positive integers, number 1, number 2, number 3. And as n increases, the electron's energy and its average distance from the nucleus is also going to increase. And if you think back to the Bohr atomic model, it's pretty easy to see. If you remember, we had the nucleus in the middle and all the orbits of electrons are on the outside, and if we assign them integer values, you had n equals 1, n equals 2, and then they would continue to go up, n equals 3, n equals 4, etc., etc. Now with the principal quantum number, as multiple electrons are in each level, so they have the same n value, and the total number of orbitals in a given energy level is equal to n squared. So if I am in the second orbital and I take 2 squared, I'm going to get 4 possible orbitals for that energy level. And that's going to become a little bit more important when we talk about electron configurations. Now this slide is just trying to get you to understand that there again are fixed differences between energy levels, but they're not equidistant away from each other. The distance between n equals 5 and 4 is going to be different from 4 to 3, 3 to 2, etc., etc. So there are differences that exist. Okay, now for the second and third quantum numbers, we just have to know the definitions. And this is where you're going to get, if you're going to get confused, where it's going to happen, because 2 and 3 are just tough to differentiate. I always remember the angular quantum number tells me the shape. I think angle, I think shape, and that's usually what makes the most sense in my head. Excuse me, and there's going to be a few different shapes that we have to be familiar with Really only two major ones, but there are four possible options here for shapes. The first one is S or spherical, and there is going to be one S orbital per main energy level. This top diagram here is just showing you the probability factor, where we define where electrons can be, and then if we kind of fill that in, it takes this S or spherical shape. And again, this is going to become more important a little bit later, but there's one S orbital per main energy level. And that's how we define some of that. Now for the p orbitals always come in sets of three, and they are all dumbbell shaped. And the reason they come in sets of three has to do with the 3D version. You can have one along the z-axis, okay? You can have one along the y-axis, and one along the x-axis. And when you put all three of those together, you end up with this conglomeration of three p orbitals along all three of the axes. And this is where I think of kind of the balloon idea, that that's where they exist. Now with d orbitals, they come in various shapes. You don't have to know them, but they always come in sets of 5. And that's going to be important for the d orbitals. Again, we're going to tie this to the periodic table, and hopefully it's going to help make that make a lot more sense to you a little bit later. Reposition the microphone. And then with the f orbitals, they're always going to come in sets of 7. Okay. Again, we don't even have to worry the shapes. They're ugly. We need to know that there are 7 of them. Each atomic orbital is typically designated by that principal, the first two quantum numbers. So what's the principal quantum number and what shape is it? So for example, a 1s orbital is an S-shaped orbital, which is spherical in the first main energy level. A 2p is a set of 3p orbitals in the second main energy level. And remember, the p orbitals are dumbbell shaped. Okay. Now the third quantum number, we just have to know what it tells us. It would tell us the orientation of an orbital around the nucleus. So in other words, which, for example, a set of p orbitals, are we talking about the x, the y, or the z one? Again, we're not going to have to know much about it other than what it tells us. So it tells us this exact orbital. That's why we made the analogy as to kind of the house for the magnetic quantum number. It tells us which of those 3D regions can the electron exist in, just like the number on your house address tells you which of those 3D places that your family lives in. Now this is important. Each orbital is going to hold a maximum of 2 electrons, and this is going to come into play a little bit later, but that's a pretty big factor there. Okay, the last quantum number is the spin quantum number, and that just simply talks about the spin state of an electron. Now there's only 2 possible values, plus 1/2 or minus 1/2, but in other words, what it's really telling us is that the electrons have to have opposite spins. Okay, and a little bit later, when we draw orbitals, we're going to put a line to represent an orbital, and we show electrons with paired spins as one up, one kind of half arrow up, and one half arrow down. But ultimately, again, it's just that these paired electrons have to have opposite spins. So I hope that helps, and I'll see you